is Algebra 2, Lesson 5-6, the fundamental theorem of algebra. The degree of a polynomial equation tells how many roots the equation has. You can factor any polynomial of degree n into n linear factors, but sometimes the factors will involve imaginary numbers. The degree of a polynomial equation tells you how many roots the equation has. It's easy to see graphically that every polynomial function of degree 1 has a single zero, the x-intercept. However, there appears to be three possibilities for polynomials of degree 2. They correspond to the following graphs below. Let's take a look at them. If we look at y equals x squared minus 4, you see that it has two real zeros, one here and one here. If you look at x squared minus 2x plus 1, it appears to have one real zero, which is right here. And if you look at x squared plus 2x plus 2, it appears to have no real zeros. Okay? However, by factoring, you can see that each equation actually has two roots. They just might not always be real. Okay, so let's take a look at these three equations, and I'll take a look at it by factoring them. Okay, if I was to take a look at x squared minus 4 equals 0, that's going to factor to x plus 2 times x minus 2, which gives us the roots of x equaling negative 2 and 2. It's the same two roots we had when we looked at the graph. If we look at x squared minus 2x plus 1, I can factor this as well because this factors to x minus 1 times x minus 1. So x equals 1 with a multiplicity of 2. Because 1 shows up twice. If we look at x squared plus 2x plus 2, factoring this one's a bit more difficult. It's easier if you put it in the quadratic formula. Okay. So if I put it in the quadratic formula, I'm going to have a equals 1, b equals 2, c equals 2, negative 2 plus or minus the square root of 2 squared minus 4 minus 1 times 2, all divided by 2 times 1. So negative 2 plus or minus the square root of 4 minus 8 is negative 4, all over 2. So negative 2 plus or minus 2i all over 2, which is 1 plus or minus I. Okay. So it has complex roots of 1 plus I and 1 minus I. So we can see that it has, each one of these equations has two roots. This is two roots, this is two roots because it has a multiplicity of 2, and these are two roots. This is two real, this is one real, but it appears twice, and this is two complex. Okay. So, every quadratic polynomial equation has two roots. Every cubic polynomial equation has three roots, which means every quintic has 5, etc., etc. This result is related to the fundamental theorem of algebra. The German mathematician Carl Friedrich Gauss is created with proving this theorem. Basically, it says if p of x is a polynomial of degree of n being greater than or equal to 1, then p of x has exactly n roots. So n is 6, it has 6 roots. N is 7, it has 7 roots. N is 4, it has 4 roots, including multiple and complex roots. Okay, so using the fundamental theorem of algebra, what are the roots of x to the 4th plus 2x to the 3rd minus 13x squared plus 10x? Okay, the degree of this 4, okay, has a degree of 4, so it has 4 roots. Not sure if they're real, complex, a combination, so we have to figure that out. Okay, so let's look at first of all, I'm going to look at it and say I can factor out an x, can't I? They all have an x in common. X, 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 x. I'm going to take an x out of this. And I'm going to get x to the 3rd plus 2x squared minus 13x minus 10. So I know that x equals 0. I know one root is 0. I have one root. Woo! I only have to find 3 more. Okay? Once I've done that, I'm going to look for the possible rational roots. Okay? The possible rational roots are the factors of negative 10 over the factors of 1. So I have plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10, because everything is over plus or minus 1. Over 13 and 10. So my possible roots are plus or minus 1, plus or minus 2, plus or minus 5, plus or minus 10. Okay? So I'm just going to start checking these and testing them and see which ones are roots and which ones aren't. Okay? So I'm going to take test 1 to start with. So I'm going to test 1. So I'm going to have 1 to the 4th plus 2 times 1 to the third minus 13 times 1 squared minus 10 times 1. So that gives me 1 plus 2 minus 13 minus 10. All right. So if I look at that, I get, oops. Yeah, so I get 1 plus 2 minus 13 plus 10, not minus 10. Oh wait. That's good. So it should be 2 minus 13 plus 10. So if you look at that, that equals 0, doesn't it? So I now know that 1 is a root. So I now have 2 roots. Right? 0 is a root and 1 is a root. So if 1 is a root, and I have this factored form, right, because that's the factored form I found that 1 was a root of, I can take and use synthetic division at this point in time. So I'm going to divide this in, so I'm going to have 1, and that's going to go into 1x to the third, 2x to the second, negative 13x, and positive 10. Why do I keep saying, oh, that's why I wrote this down there. It should be positive 10. Typo. No wonder I'm messing myself up. Alright, so if this is the case, then we just need to bring this down. So we're gonna just do synthetic divisions. This is 1. 1 times 1 is 1. 3. 3 times 1 is 3. That's going to be 10. And this could be 0. Okay. So we know 1 was a root. So now when we get down to that point, that was coming out of a cubic. So this becomes quadratic. So this becomes x squared plus 3x minus 10 equals 0. So now I'm going to look and say, can I factor this? Thank goodness I can. Or I can always put it in the quadratic if you can't remember how to factor very well. If I factor this, I'm going to get, I need product of negative 10 and a sum of 3, so that's going to be positive 5 and negative 2. So x is going to equal negative 5 and positive 2. So my other 2 roots are negative 5 and positive 2. So all of my roots are right here, 0, 1, negative 5, and 2. So what you do is you try to figure out what your possible roots are, test them. Once you can get it down, you can start using synthetic division. And once you get it down past synthetic division, you can get it all the way down to the quadratic formula and solve it. Now, there's another way of doing this, which is slightly similar. You can find all the zeros of a polynomial function by using some combination of graphing, the factor theorem, polynomial division, and the remainder theorem, and the quadratic formula. So if I wanted to find all the zeros of the polynomial function, x to the fifth plus 3x to the fourth minus x minus 3. First thing I'm going to do is, I know there has to be 5 zeros. Okay? There are 5 zeros because my degree is 5, so I have to have 5 zeros. Okay? I'm going to use my calculator to find any real roots. And I'm going to use my calculator to find the real roots. So I'm just going to stick in my calculator that particular equation and graph it. So if I graph in my graphing calculator x to the fifth plus 3x to the fourth minus x minus 3. Okay. I can read directly from my graph. This is a nice one because I can read it right off the graph. Okay. I use my x and my axis. My graph kind of looks like this. It looks like I have a line here, and then I've got something that looks like this. But it happens to be going through my graph. Okay. If I look at my graph on my x-axis, it's crossing at negative 3, negative 1, and positive 1. Negative 3, negative 1, and positive 1. Those are my real roots. Those are the roots that I can find by graphing. Now, I need to find all my other roots. Okay. Since negative 3 is a root of this equation, I'm going to use negative 3 using synthetic division. Right? So I'm going to use negative 3 as a real root. And I've got 5, 4. Notice there's no 3 and there's no 2. So I'm going to have 1x to the 5th, 3x to the 4th, 0x to the 3rd, 0x to the 2nd, negative 1x to the 1st, and negative 3 is my constant thing. Okay, so if I break this down, that's a 1. 1 times negative 3 is negative 3. That's a 0. 0 times negative 3 is 0. That's a 0. 0 times negative 3 is still a 0. That's still a 0. 0 times negative 3 is still 0. This is negative 1. Negative 1 times negative 3 is positive 3, and this is a 0. So we end up with, if you remember, right, this was a 5th. This is one of the factors, so this becomes a 4th. So this becomes x to the 4th minus 1 equals 0. I can now factor this. Right? I can factor this to become x squared plus 1 times x squared minus 1 equals 0. Right? X squared plus 1 equals 0. X squared minus 1 equals 0. So subtract by 1, x squared equals 1. Take the square root of both sides. X equals plus or minus I, because the square root of negative is I. Here I'll add my 1. So I get x squared equals 1. Take the square root of both sides. I get x equals plus or minus the square root of 1, which is 1. Which we already had. So we already had those earlier. We just confirmed them now. So there's our other 2 roots, because we had the first 3 roots. So there's 3, negative 1, and 1. Now we can add I and negative I to the mix. So there's all of our roots. It's a little easier if you can use your graphing calculator, because it does eliminate a lot of the testing of the possible rational roots. But you're still going to have to do both on your test, so it's good that you're familiar with both of them. All right, the other thing that you have to be able to do is you have to be able to look at an equation, state the number of complex roots you're going to have, the number of possible real roots, and the possible rational roots. Okay, so if I'm giving you an equation, you should be able to remember complex roots means real and imaginary roots. It means all of the possible roots. Okay, so when you see the word complex roots, it doesn't just mean roots like I and negative I, or the square root of 3 and the negative square root of 3. It means what are all your possible roots. So if I'm looking at this first one, 2x to the 4th minus x to the 3rd plus 2x squared plus 5x minus 26, my complex roots, since it's a degree of 4, I have 4 possible complex roots. Okay, degree of 4, so there are 4 roots. Okay, real roots, remember, with the real roots, it's either going to have the same as this, or it's going to go down by 2 each time. Okay, so it's going to either have 4 real, 2 real, or no real. Okay, 4 real, 2 real, or no real roots. The possible rational roots. The possible rational roots. Remember, that's going to be plus and minus. I can do this better. It's going to be the factors of 26 over the factors of 2. Okay, 26 plus and minus 1 plus and minus 2 plus and minus 13 plus and minus 26. Factors of 2 plus and minus 1 and plus and minus 2. So, obviously, all your possible rational roots, if you want to write them in order from smallest to largest, you can, but I don't have a preference whether you write them in ascending order or not. Since all these numbers can be written over 1, our possible rational roots are plus and minus 1, plus and minus 2, plus and minus 13, and plus and minus 26. Then I could have 2 over 1 and 13 over 2. Right? Between 1 over 2 and 13 over 2. Right? So I could have plus and minus 1/2 and plus and minus 13/2. Because basically you're going to say plus and minus 1 over 1, which is 1, plus and minus 2 over 1, which is 1, plus and minus 13 over 1, which is 1, and plus and minus 26 over 1, which is 1. And then you do plus and minus 1 over 2, plus and minus 2 over 2, which is 1, plus and minus 13 over 2, and plus and minus 26 over 2, which is 13. So you just put all those numbers in there. So you get 4 complex roots, 4, 2, or no real roots, and our possible rational roots are plus and minus 1, plus and minus 2, plus and minus 13, plus and minus 26, plus and minus 1/2, and plus and minus 13/2. Okay, let's look at the next problem, which I'm going to have to erase part of the last problem in order to get to. So I hope you have this written down. If not, you're going to have to go back to the video. But that's okay. That's why we do videos. All right, so this is a degree of 5, so it has 5 roots, 5 complex roots. Okay, so I could have 5 going down by an even number of 3 or a 1 in a root. Okay. And remember, it's going to have 5 because they have to occur in pairs for certain things. So we're going to go down by 2, 5, 3, or 1. Okay. Possible rational roots. Okay, we're going to have the factors of 18 over 1, which means we're going to have possible rational are plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6, plus or minus 9, and plus or minus 18. I love it when there's no denominator, because then you'll just have to do the factors at the top, which is 1 times 18, 2 times 9, 3 times 6. Okay, so those are all your 5 complex, 5 clear, 1 real, and your possible rational roots. A nice little summary here. Here are equivalent ways to state the fundamental theorem of algebra. You can use any one of these statements to prove all of the other statements. Every polynomial equation has a degree of n greater than or equal to 1 has exactly n roots, including both full or complex roots. Every polynomial of degree n greater than 1 has n linear factors. And every polynomial degree function of degree n greater than 1 has at least one complex zero. Okay. So there we have it. That is the fundamental theorem of algebra all summed up.